Good morning, everybody. Now I'm on camera. Good morning, everybody. Thank you for joining us today. We're excited to have the culmination of the summer's work by some amazing high school students and mentors and faculty hosts, all working together to make some magic this summer. So we're looking forward to seeing what you've all developed and worked on, and it's going to be a fun morning, and thank you for all being here. And we're going to have a little bit of a break between each session just as we reconfigure the ADs. So feel free to get up and grab some refreshments and and make yourself at home. So we're going to go ahead and get started with the Prince group. If you guys want to come on up, introduce yourselves, and we'll learn about what you studied this summer.
I'm Victor Saldana, and I attend John Mayer High School.
I'm Nishikawa, and I'm going to be a senior at Marshall Fundamental.
And this is our final presentation on near-Earth objects with ZTF.
Over the past 6 weeks, we learned about near-Earth objects and how they are observed and why they're important. We also learned about how to scan asteroids and what we do with good candidates, as well as how astronomers utilize Python code in their work and how ChatGPT can help create this code.
So first, before diving into this slide, I just want to provide some background information about how our universe was formed. So pretty much after the Big Bang, there's just a ton of dust floating around in space. And pretty much that dust eventually became our solar system. It became our planets, our sun. And that remaining dust became these asteroids. And there's a large concentration of asteroids between Mars and Jupiter. So first, what is a near-Earth object? It is an object that is classified to have a perihelion less than 1.3 astronomical units. In space, things don't really orbit perfectly circular. As you can see, it's more of an egg shape, and the sun is not in the center. And this distance from the sun to the side, to the short side, is called the perihelion, and this long side is called the aphelion. So near-Earth objects are objects with a perihelion less than 1.3 astronomical units. An astronomical unit is a unit of measurement used by astronomers that is equal to the distance from the Earth to the sun. And all near-Earth objects are either asteroids or comets.
Many people don't know the difference between asteroids and comets or believe they're the same thing. We learned that asteroids are made of...
Yeah, speak a little, it needs to be a little closer to your face. Yeah.
We learned that asteroids are made up of rocky debris and are commonly found in the asteroid belt, and comets are icy and dusty, and when they are close to the sun, they emit light. The comets also have two tails, the dust tail and ion tail, and both near-Earth asteroids and comets must have a period of just a few years.
So many of you are probably saying, cool, these are just...
I'm sorry, can you come over here and then you can share the microphone? Thank you.
A lot of you are probably just wondering, like, these are just rocks in space. Why should we care? And there's two large reasons why we should care. The first is that they're the building block of our universe. As said before, they're made of the same dust, and very crucial to our understanding of how our universe works. And secondly, which more people care about, is one day an asteroid can hit Earth. As of now, we really don't have any way to stop it. And as you can see in this histograph, so the blue represents the total amount of near-Earth objects that we have found, and the small concentration in red is the amount that are potentially hazardous. And what exactly makes them hazardous is if they come within 0.05 astronomical units of Earth's orbit, which is roughly 4.6 million miles, which in our understanding of distance is a lot, but in terms of space is not really a whole lot. As well, if its absolute magnitude is greater than 22, so The lower the magnitude, the brighter the near Earth object is, and the lower the magnitude, the larger its diameter.
We also learned about the Ziki Transient Facility. So it's a 48-inch telescope at Palomar Observatory here in California, and it was built in 1948, and for years it was the largest Schmidt telescope in the world. A Schmidt telescope is a type of telescope that has a mirror at the bottom of the telescope and a lens at the top to improve image quality. And as you can see in this picture, ZTF has a very large field of view compared to other known telescopes, and it can scan the entire northern night every few days.
So there are two primary ways that ZTF scans for near-Earth objects. The first is called Z-streak. Because asteroids are moving so fast, when you take a picture of them, they obviously don't come out still. As you can see in the top image, that is a picture of an asteroid. It's moving so fast, the camera can't capture it still, so it leaves a streak, and that's how we're able to identify them. And the other method is called Z mode. This one works with slower moving asteroids. It's pretty much looking at several images of the same location in space and seeing if there's a repeating object, a reoccurring object, and seeing if it's moving slowly. In figure B, you could see these are several images stacked on top of each other, and you can see the same object moving slowly.
So what happens after a good candidate for an asteroid is found? So first, we have to look to see if there's a second image of the streak, and we then have to rule out satellites of, or like potential satellites of these asteroids by checking with known satellite positions. And if no satellites match the streak, then we have to send it to the Minor Planet Center, and we have to continue observing the streak. And this after this, the streak is given an initial name, and only after years of observation is the asteroid given a permanent name. So Victor and I stayed up on July 25th to search for streaks. We looked in over 600 images, and using our knowledge, we determined if a streak could be a good candidate for an asteroid or not. And in these 600 images, we only accepted 15, and 0 of them turned out to actually be asteroids. We checked to see if the accepted streaks were already known objects, and they all were.
So from the very beginning, me and Emma both wanted to implement programming into incorporate it and somehow apply it to astronomy. And we ended up having an even better idea, which was to implement ChatGPT. ChatGPT is one of the most talked about inventions. I'm sure all of you are familiar with it. And we decided to use its capabilities of writing code to do stuff for us pretty much. So we asked it 2 questions, and the first was to calculate the orbit of an asteroid given its initial velocity and position, and to secondly determine the asteroid's type and its orbital elements such as its period, eccentricity, and other stuff given its name. So what we learned from this exercise is ChatGPT is extremely powerful but not perfect. It took us like 95% of the way there, and as you can see on the figure all the way to the left, right, we were able to get the orbit of the asteroid down. It just needed some minor tweaking, and then we were able to get the code where it pretty much just spits out a ton of data eventually to work. I think the thing wrong with that one was it was just using an outdated database, but it pretty much got us all the way there.
So what can you take away from this presentation? That near-Earth objects are important to research and as well as difficult to research. It is important to look for asteroids because they could be hazardous, and that technology can really help us with our work and hopefully can improve in the future as well. Thank you.
Thank you.
I'll introduce Zach. One of your 2 mentors is here. Zach, do you have any comments on how the summer went? I don't want to put you on the spot, but.
Yeah, it was definitely fun. I think the two highlights of the summer were actually getting involved in the scanning during the night. They stayed up until like from 10 to 2 a.m. Looking at live data incoming from the Suzuki Transient Facility and projecting, accepting stuff. And then also using ChatGPT was a very interesting experience. I think both for them and for us as mentors, learning a bit more about the capability of this in the world of astronomy is very relevant nowadays. But yeah, I think they did a great job and very proud of them. So,
Thank you.
yeah.
And their other mentor, Kumar?
Yeah. It has been fun, like really, getting to mentor their involvement was really fantastic. The way at their level, like doing this kind of a work is really good, and they've done their best. So it's fun.
Thank you. Any questions?
You know which libraries you use for the Python code?
We use the NASA API.
That's
Where did you guys get the scanning data
From the ZTF database.
You both, how do you feel about astronomy as a possible field of study after this?
I think because originally both of us, originally we had zero experience in astronomy, but after this, I don't know about you, but I'm definitely interested in continuing in this field.
Yeah, like I didn't really know anything about astronomy. I think it's really cool, but I can't really see myself going into all this. I think it's cool. I love learning. It was a really cool experience, but I can't see myself doing all this.
Thank you. Well, that's what this is all about. You find out these are things I might want to continue with. These are things I've explored and want to try something else. So at this age, that's exactly what we want to hear. So thank you.